All right, we finished Obadiah quiz. How many chapters does Obadiah have? So there's one. So that's why there's no. Yeah, anyway. Then we've done Jonah, we've done Obadiah. I'll probably assign for the next lab to do. We can move on to the minor prophets because it's Amos, Obadiah, Jonah. So you can go just to Micah, do Micah, Nahum, Habakkuk, etc. Okay, but don't worry about that yet. A few reminders. I'm surprised that I still have to tell a bunch of grown adults kind of stuff, but check. Sometimes I can tell whether or not you actually go check your grade on D2L. That's something that I don't know if students are aware of, professors can see. We can actually see if you're not only submitting stuff, but then whether or not you are clicking on the notification or seeing that you actually got feedback. So just check your grades, do basic things like that, check news items, etc.
Does pulse count?
Pulse counts, but check details because sometimes pulse can't process something that goes into the website. But just in general, things like that, just don't forget to check D2L. I mean, I shouldn't have to say that again, right? So, all right, let's get to the lecture. I like chapter 15 a lot, because we're about to find out in about 2.5 weeks how many of you should have failed Calc 1. Wow. Just because here's the thing. So I've had different teaching philosophies on this in the past, and so far I've always failed. And here's why I always failed. It's because I went into teaching Calc 3, reteaching Calculus 1. This is Calculus 3. If you don't want to do Calculus 3, just drop the class. Okay. I'm not going to teach you Calculus 1 and Calculus 3. So I'm going to assume proficiency and A-level proficiency of Calculus 1, which means if there's a derivative rule, I'm just going to do it. I'm not going to explain it to you. Why? Because Calc 1 happens freshman year, okay? So that's gonna help lectures keep flowing because what happens is Calc 3 has plenty of volume to get through. So if I'm trying to cover Calc 3 volume at the same time reminding you of Calc 1 stuff that you just are too lazy to, finally learn, then that's not my route, okay? So get a proficiency of Calc 1 up. It's okay to repeat those things. It takes time. Again, I took Calc 1 6 times. It takes time. And that's okay. Just make sure you're being intentional about that. So I posted, I think, on the D2L, a whole document. And so everything on that document is assumed knowledge, and I'm going to assume you're comfortable with everything on the document. It's basically high school Calc. So it's Calc BC. Because if I'm able to do that, lectures are going to be a lot easier for you guys and for me. And because we can focus on the Calc 3 concepts instead of rehashing what a parabola is and how to factor and what the derivative is of sine, things like that. Okay, so do you all remember what a limit is from Calc 1?
Yes.
Okay, so then what I'm about to write should be completely expected. If we take a limit now, instead of just on the real line, but in a plane, so a point to a point of a function that takes in 2 variables, if that approaches some L, then that can be true if and only if for all epsilon greater than 0, there exists a positive delta, so delta greater than 0, such that the magnitude of P naught less than delta implies that the difference of fxy y minus L, that's less than epsilon. Okay, this is the definition of a limit, just extended now to a norm, P naught, instead of an interval x minus a, being less than delta, and then that's going to give that your difference between the function and your limiting value remains less than the positive epsilon. All good? This guy? This in English, this means that. And this means implies.
So the symbol to the left of implies.
Delta?
Oh, yeah.
Yeah.
Oh, that's delta.
That's delta. Oh, this one, you might not have seen this one, so I'll put that here for, um. And this one, I should probably clarify. This. There. Exists. Okay. Raise your hand if this is familiar. Oh, no, okay. Well, make sure it's familiar by tomorrow, okay. This is the definition of a limit extended to a point. Now, the way that you're used to seeing it is not necessarily with points p naught, though. What you're used to seeing is in Calc 1, the limit as you take x approaching some a of your function, if this is equal to what you're limiting, then instead of taking a norm in 2 dimensions, and I'll hand draw this so you can see. We would take all the epsilons that are positive. There's going to exist a delta greater than 0 such that instead of doing the norm, we take a norm kind of on the metric topology of the real x minus a less than delta. So that difference on the x-axis, and that gives you your difference of f of x minus l. And this is Calc 1. And Calc 3 is pretty much the same exact thing, except for we have 2 variables. We use points instead of being restricted to a single real number. And then we're using the norm instead of the difference x minus a. All right, cool. So this is limits. Now I'll do this. So recall what this looks like on, I'll show you the Calc 1 version so you can kind of extend the idea. So here is like an x-axis, right? And so if here is some a that we're trying to approach, what we're saying is, okay, x minus a needs to be less than some delta. So I need to choose some positive delta. So up here, I can shift up by delta. If I take a, I add delta, I get a plus delta. If I subtract delta, I get a minus delta. And this is going to give me that interval of x minus a, my absolute value is less than delta. And then we have some x value, right? Regardless of what that x value is. And this x value is what we're trying to push toward and approach a. And so we observe here that the difference between x minus a, so this distance between x and a, is always less than delta, right? Because delta is the distance. That's delta distance. That's delta distance. So we have this distance staying less than delta. And if that's the case, then what's happening up here in the function stuff is then we're staying under epsilon. But we're interested in the input space right now, because that's the main difference between the points and x minus a. Okay, thumbs up, that's good. So we're going to extend this idea into the plane. With 2 variables in the function, that means your input is now a point in Cartesian space. So we can expand this, and we have some, here is, this is not a graph. What I'm going to show you is the input space. So whereas we used to describe the input space of a function as just a line of real numbers, now we need 2 coordinates because we can put 2 real numbers into this. So the first things first is if we have some sort of a fixed delta, it's going to kind of serve as a radius away from the point P naught. So the shape of the region we're going to get is circular. Ooh, that was pretty good. Okay, and so here at the center of this circle is what we're trying to approach. So the center is P naught, which we can call A comma B, right? Give it some coordinates. So this would be A. This would be B. So that's kind of the P naught that we're trying to approach. Same idea to fixing some A that we're trying to approach. And then now instead of delta being restricted to just going on, because notice on the x-axis, you can only either go to the right or you can go to the left. That's it. But now that we're in a plane, I could go an infinite number of directions away from this point. So this idea of there being, have you ever heard of radius and convergence? The answer is yes, if you took Calc 2. When originally that doesn't make much sense because you say, what about this is a radius? We're on a line. Well, the idea is, when you extend the number of dimensions, this radius is actually describing all the points that are equidistant from a circle. So this now, this distance is our new, how we express our delta. And so that's kind of what we mean by we're gonna draw this in keeping it less than delta. So any point inside of this kind of dotted region, right? So for all of these deltas that we choose are positive, if I have some point like this, some point, and this is functioning as the x, so this is some xy, it's a variable. Difference between the variables versus a chosen constant, this is the fixed constant, this is the variable one. In the same way that a is the fixed constant and x is understood to be the variable here. And so that's the relationship between everything, right? Because now we see the distance between this as this is trying to approach our point, that p naught is less than delta. I think delta is the radius we're inside.
When you say PP not being effective, or
The distance between these 2 points. Vector would be given the vector notation. And so this is where, again, notation does matter because they will communicate nuance, like slight nuances between the different. So even though I drew an arrow, this is not a vector arrow. This is indicating we're like a direction, kind of like we're pushing that point further limit. In the same way that I would draw an arrow saying that x is going to go to the A. Right, so we're not going to choose some random x out here when we do calc 1. We're also not going to choose a random point like out here. Whenever we fix for every single positive delta, we'll always be able to find, so that now that context-wise this, right? So for every single positive epsilon that we choose, we're able to find a circle like this, a circular region like this with radius delta, such that all of these norms between what we choose and the point that we're approaching, so long as that stays within inside of our circular region with the radius of delta, then what's going on in the surface is that the function values are all going to be less. When we subtract with the limiting value, will be less. In other words, to go to 0. So that is the extension. And you could do this generalized to an arbitrary number of dimensions if you really wanted to, because norms are powerful. Imagine if the input space was 3-dimensional. So now that delta is not just describing, so here we're stuck on left and right. Here we're stuck on a circle in 2 dimensions. Throw that into 3 dimensions, suddenly that point is the center of a sphere with a radius of delta. And then you're choosing points inside of the sphere to do limiting for some other function. But this is technically, you can generalize this because norms are generalizing. So, are there any questions about this? Okay. Next little subsection of this is much easier because it's just going to recall all of the limit laws that we're allowed to use. I'll just say goodbye to all the lovely symbols and start using numbers again.
I'm sorry for you.
Okie dokie. So in general, instead of, how in calc when you get used to seeing limit as x approaches a or something like that, the form now is going to be limit as p goes to p naught, where it's understood that p is a variable point xy, p naught is like that constant fixed thing you're approaching. Sometimes it's given explicitly as xy going to ab, but p naught allows you to say things about any number of dimensions really, so it's more powerful. So here's a theorem. The limit clause. The reason I like showing that this is a theorem because a lot of people think that someone just made these laws up one day. No, these were proven. We don't go over the proofs for all of these because that's what calculus 4 is all about. But what we're going to do is we get our ingredients. So let the limit as p goes to p naught of a function of 2 variables. So we'll specify 1 or 2 for the input space. If that's equal to L, and if I have another limit as p goes to p naught as well, but of a function g, x times. Then this is approaching m. And then we'll just specify, for the sake of technicality, that L, M, we have another constant C. Those are just going to be scalars, so constants in R. And also we want N to be a positive integer. And so from here, we get our limit rules or limit laws. So the first one is the easy one. It's just that the limit as P goes to P naught of F either plus or minus, it doesn't matter, is just going to be L plus or minus F. Straightforward enough. And if you really think about it, if you just change this P and P naught to X and A, then you pretty much just have the calc one limit laws again. So this isn't supposed to be something shockingly new. It's just all analogous to what we've already done. The limit as P goes to, oh, sometimes we call this the sum and difference rule. Or you could just use it without citing what it's called. And P naught, if you have a constant multiple times your function, you just take that constant multiple as expected and multiply it by that limit, what it would be. So this is kind of the same idea as if we took the constant outside the limits. That's why we can take constants outside the limit, but you just take it, multiply. Is the what?
The thing, on top, on the first one, yeah.
Here?
Yeah.
Yeah, L plus or minus M. I'll rewrite that so it's clear. And then now we got the limit as P goes to P naught of now products. So if I take the function f, I multiply it by the function g, then we just multiply what those limits are going to be. Take L times. Same thing goes for quotients, which will be f over g. F over g. And this will be L over M. So now we just got to specify that we don't want M to be 0. Say M not equal to 0. And then the two ones that people forget about are 5 and 6. 5 is, it's kind of like a power rule for limits, in the sense that if you take the limit as P goes to P naught, if you have a function that's been raised to n, and recall that n has to be some positive integer, so this is just like a power, so like f squared or f cubed or f to the 4th power, then you can just take whatever the limiting value is supposed to be and raise it to that power. And then if you can do exponents, you can also do radicals, which is fractional power. So E goes to P naught of f1 over n. So we get L1 over n. Notice we don't need to mention that n can't be 0 because that's already been taken care of here. It's assumed to be just some positive integer, but we do need to accommodate the fact that we can't take the square root or even power root of, an even root of a negative number. So in the event that n is even, then that just tells us that we need L to be positive in order for that to work. Because otherwise it'll take something like the square root of -5, but that's not happening. Anyways. Okay. So there we go. First thing I know is jumping into ice water, so that makes this feel way less horrible. Question? Okay, makes sense? So we do all this so that we can actually just compute limits. So let's do that. Actually, yeah, I can fit it right here. You can see all the rules. I'll do the example right here. Okay, so the limit as I'm going to give it as xy to 2, 8. So that this is kind of how you'll apply it instead of just staying in P and P naught. So this is the P, it's the P naught of 3x squared times y plus the square root of x times. And give everybody a chance to write that down. So you should get just 3 times the x value squared. Because 2 is x, 8 is y. So then if we're doing 3x squared y, I need the y value here. Plus the square root of 2 times 8. So 3 times 2 squared times 8, add on to 16. If you could solve this on your own, raise your hand. Sweet. Let's move on to some Calc 3 specific stuff. Actually, what's great is now that I'm doing some topology, I'm recognizing that it's kind of an allusion to topological things, but it's just at a lower level of abstraction so that you can interact with it computationally. Here's something that I didn't know, and I would have appreciated knowing when I was a freshman math major, is that sometimes the definitions you're given in a math class aren't the definition. It's a definition, that's a valid definition, but it is given in the context of what level of abstraction and language you've developed to that point. So if you do the double major in math, you're going to redefine what functions are about 6 times before you get to a satisfactory gen ed graduate level understanding of what a function is. And then you keep redefining it, it gets more and more abstract, and so you're like, whoa, rainbows and butterflies, and it's pretty great. Okay. Oh, you know what? If there's time in class, I'm gonna show you how we've defined equals. Because equals is my favorite thing is equals, the equal sign is a subset. The equal sign is a subset. So every time you see that symbol, it's describing to you a subset of objects, and we'll talk about that. Okay. Let R be a region in R2. So an interior point use your intuition for what that possibly might be in a region R. P of R lies entirely within R. And a boundary point Q of R lies on the edge of R. So we would say that a region is open if it consists entirely of interior points. And then also a region, we have open regions, we can have closed regions. So a region is closed if it contains all its boundary points. So in the abstract, that's a lot of words. But there's this idea that if I have some region, and I call this region R, there are 2 different kinds of points, at least involving this region. There's more than just 2 kinds of points, but for what we're interested in here. So if I were to choose, say, this point right here, interior or boundary?
Interior.
Right, why is it interior?
It's just in the boundary.
Yeah, because it's in there. That's a pretty good reasoning. Now, the way that we would do this in I'm not going to show you the whole thing, but the hint at how we formalize this idea is we say, for all circular regions around the point, such a subset will only contain points also in R. So that's how you can know it's in the interior, because no matter how small I make the circle, I can always, there's always going to be one such circle that will only contain points in R. So this is interior. Well, say it's near the edge, right? So this is pretty close to the edge, right? However, does there exist a circular region where this is the center, such that you only have points that are in R?
Yes.
Yeah, so you just choose a smaller one. So instead of choosing, maybe this is a pretty big one, you have a lot more freedom there. There still exists, I guess I'll call this P1 and P2. There still exists an interior point in it. Or you get to choose how big. Now, here's the thing though, is it even can you find a way to choose a circle of any size such that you only have points inside of the region right here? Well, I didn't say semicircle, I said circle. So it's got to be a circular region graph. There's no way, regardless of how small you think you might be able to make this radius, if it's right on the boundary, every single circular region around this has to contain points that are not in R. So, and because of this, even if I made this infinitesimally small, getting close, I'll still always have, there will always exist at least one point outside of R. And so this is, but there's also points in. So we would call this a boundary point. Now, really what we're trying to do is we're trying to expand this idea of open and closed intervals to regions, okay? So if I were to show you, I mean, this should be familiar, right? So open interval AB in the real line is the set X values that A is less than X, right? So that's just common sense. This is what we're already used to having. And then a closed interval would be, well, just where what's the only difference between the open and closed here in the real line? Yeah, we contain the boundary point. So we could consider now when we only have a one-dimensional thing going on here, right? So if this is A, if this is B, and we have the points inside, then yeah, it's pretty easy to see, okay, if I just stay inside this interval, whether that's open or closed, the boundary points can only really exist on two directions. So interior points would be anything like that. That'd be an interior point. And the boundary point is going to be A, and the boundary point is going to be B. And so that's how we have this is open. This is open because we're excluding those boundary points, which means that every single other element though in this set acts as an interior point. So this is alluding towards something we call supremum and infimum, but that's for a future semester. Closed. Now we're including those boundary points. And so we have, and so when we expand that to R, think of the same kind of thing. Is that normally what we'll do is we'll do a hard line to show closure. So in the same way that we have hard brackets instead of the parentheses to include everything, we'll use a solid line to imply this and a dotted line to imply open. Because when it's dotted, we're not including the points that are actually, we're excluding these boundary points from what we're including in the region R. And so now the only possible points that you have in R are your interior points. You can't have a boundary point here. So this is an open region. This is a closed region. This is an open region because we're now excluding the only boundary points that we had. This is a closed region because we're including those boundary points as part of R. Okay, make sense? So the reason we talk all about this is because when you take those limits, sometimes in your domain, kind of in your region, the question is, can we take limiting points if that point that we're trying to approach is in itself a boundary point? All right, so we make that consideration, and then we'll do an example here. And what you'll find is that this consideration is kind of analogous to removable discontinuities with just functions in the plane. Let's erase. You're good if I erase this? Okay. All right, so let's do example. With the limit. XY is approaching the point 4, 1. And the function we're interested in here is a xy minus 4y squared in the numerator. In the denominator, it's going to be the square root of x minus 2 times the square root of y. Now, first glance says, okay, well, you should always try to just plug it in. Because if it ends up working, then work smart, not hard. The only issue is plugging in is going to give me 4 minus 4, 0. 2 minus 2 times 1 is 0, 0. So you'll get an indeterminate form. And the indeterminate form of 0 over 0, which is a meaningless mathematical thing. So this means that we need to algebraically simplify this. Do you guys know the algebraic simplification is with it?
We can move it.
Oh,
And then shift the fraction to square root. Yeah, because it's the negative.
someone said it. Rationalize denominator. So what's the conjugate?
Plus 2. Oh,
Because now we have the limit as xy goes to 4, 1 of, and then we could actually factor this. So if we take out one of the y's, we get y times x minus 4y. Everyone see that? And then times now this, the square root of x plus 2 times the square root of y. Now, difference of squares kind of factorization here. So square root of x times square root of x is a. Cancels, cancels, minus 2 times 2, and then root y times root y. Now, if you can't see why we did this, then Lang is teaching. There's 2 sections of Calc 1 going on right now, so you can audit. xy goes to 4, 1 of y times the square root of x plus 2 times the square root of y. And now there's no issue with substitution. We have something we can plug directly into.
Will, is there a way to do multiple or not? Or is that later on?
Well, L'Hopital, so the thing is we have multiple derivatives, and that'd be, I think L'Hopital only works if you have a function of one variable. Because then the question is, perhaps there is some sort of a form of L'Hopital's rule that deals with multivariate functions, but that involves partial derivatives. And then I'd have to wonder if what order you take the derivatives, and then if that order matters, and if it changes the limit on accident. Hey, you know, that could be your homework for the next lab. You can find the form of L'Hopital's with partial derivatives. But I'm pretty sure that L'Hopital's is restricted to, I could be wrong about that though, I just never looked into it. I mean, yeah, look it up. If you find something, let me know, because I'm kind of curious now. But as of right now, just use the algebraic simplification. Because this is far easier than having to do derivatives of square roots anyway. And then if we plug this in, we get 1 times the square root of 4 plus 2 times the square root of 1. Which is just 4. All good? All right. So be prepared. So this would be a boundary point on your region, and you have a removable discontinuity that you get rid of by the rationalizing the denominator. So pretty much just apply all the techniques you already know to limit here. So you might not get on the exam, you might not get a rationalization, you could. You might get a factorization. You might get any of the algebraic techniques that you did in Calc 1 made analogous to just expanding it to 2 dimensions or 3 dimensions. Okay, but there is something that is important to talk about is we can approach different things. And so limits can fail to exist, of course, with these kinds of limits. So I'll show you this test. It's called a 2-path test. And if there's anything that's probably the most important part of this section for future reference and wink is the 2-path test. This is kind of the most important part of limits in terms of calc 3 because it's different. It's a general idea, and it's also just really pretty that we have this. So 2 yeah. And for the non-existence of limits. How many more stars do I need to put on this to convince you that you should pay attention for this portion of class?
2 more and more.
I think you put one, 2 more at the beginning, so it's.
One more.
It's sparkly now. Okay, so this is how it works. If F approaches 2 different points, so 2 different points as P goes to P naught along 2 different paths in the domain of F, then the limit as P goes to P naught of your function does not exist. Now, I'm going to have you recall something. Calc 1. Does the limit as x approaches a exist for this particular function?
No.
Why not?
Discontinuity.
Jump discontinuity. And more specifically, what is the left-handed limit is different. So basically you approach different values. So if you approach if your function approaches 2 different values depending on the direction you go, no good. That's all this is saying. Now, of course, we've expanded it so that instead of being restricted to approach a point from only the left side and the right side, this sucker's got to be approachable in R2 from an infinite number of directions in every single possible path. So limits existing with surfaces is far more restrictive than limits existing in plane. Because here we only got to go left and right. That's the only directions, and you can always verify that. But you can never essentially account for every single direction in a circular region. But here, so your function, and here's now, I'll draw another point, try not to assimilate. So now this is an input space, x, y. So this is input. So this is calc 1, I'll separate it. Now we're talking about the input space for a function that is a surface in 3 dimensions. And so here is, again, remember we set this up with a delta. So here's the point P naught, and this is kind of like your delta, just to ground everybody where we're at. Now, what this means is all the paths that get from this little region into P naught has to approach the same thing. The same idea as approaching left and right. So if I take a path that looks like this, it should approach the same thing as a path through this domain that just goes straight shot from there to there. And which should be the same thing as this path. Every single possible path that you could take through the domain of the input space to get to that point needs to all approach the exact same thing. Because if you don't, your surface is going to have something wrong with it. It's going to be approaching 2 different things or have some sort of removable discontinuity, etc. So this is easier to visualize because it's stuck in the plane. This is not as easy to visualize, but that doesn't change the concept. The idea is intuitively the same and analogous in extension. Does that make sense? Yes. And because there's infinite paths, that clarifies that this 2-path test is for non-existence of limits. So don't try to use this to prove that a limit exists through paths. You can't prove that a limit exists through paths because you'd have to check an infinite number of paths.
Okay, so that we can only verify that it's not.
Yes.
That it doesn't
Non-existence. So one of the first biggest mistakes is people would take this test and try to do everything except for just showing that it's a non-existence theorem. This is only for non-existence. But don't make it do something it can't do. Like engineering is writing theology papers, they just can't do, so don't make them do it.
Yeah, I've done.
Oh, never mind. I was gonna be like saying music makers going to ORU, but non-existence. So let's go to an example of what this looks like. Because in the abstract, it's like, okay, that's fantastic, whatever. What does it look like though to actually apply and restrict a path to your limit? Because it's like, where does that happen? Does it happen in the limiting part? Does it happen in the function? So here's how we handle this with an actual function. So this limit's not going to exist, and we're going to show that it doesn't exist. This example, very important example, wink, wink. Sorry. What's funny is I can give you all the hints I want, but if you're not paying attention, it doesn't even matter. So, the limit as xy going to 0, 0. So the kind of we're in the domain point would be the origin here that we're trying to approach. Here's our function. It's going to be x plus y in parentheses, squaring that over separately x squared plus y squared. On your own time, you can throw this into a computer graphics or whatever thing to see what that surface would look like. But for now, we're just interested in showing that this limit doesn't exist using two-path test, because two-path test is for what?
Non-existence.
Okay. Convince me that the two-path test is for what?
Non-existence.
Okay, good. So we're not going to try to prove that this limit exists. Okay, we're trying to prove using two paths that what?
It doesn't exist.
Non-existence. Now, here's what we mean by path. We can choose a path. The easiest path you should be choosing is a line, because it makes the algebra far more easy. Okay. So let's just choose the path y equals x. That's a very easy path. It's just a linear path through your domain to get to your point. And see what happens. Here's how you computationally do this. Every single place you see a y, the y, we're going to substitute in x. So we get limit x, y going to 0, 0. And now we have x plus x squared over x squared plus x squared. So this is 2x up top squared. And the 2x squared is going to give you 4x squared. Just an x squared with just an x squared is just 2x squared. And actually, we won't really have to plug anything in because these x squareds are going to cancel. So we're left with. So here's how I interpret this. As we're traveling through the input space, as we're approaching it. So here we would say, okay, as I approach from the left side, I get to this function value. Analogously, as I approach the origin along this y equals x path, the surface is going to approach too. Now, what if we approach it from a different path, right? Maybe we don't want to go from y equals x. After all, it shouldn't matter, right? It should always approach the same thing. So it's now, I'll call this path. And now let's choose, what do you guys want to do for the other path? Yeah, we could do 2x, that's a good one. And to clarify, it would be impossible to make that z, because z is the output. That's like the actual surface. So we're talking about the input coordinates right now. So this is our second path. Okay, and then let's see what happens. So the limit as x, y goes to 0, 0. We have x plus 2x is now y squared over x squared plus y squared. So take this and square it. It's going to be 4x squared. So x plus 2x and the numerator is 3x. Not 3x squared is 9x squared. Over, we have one of these and plus 4 of them. So it's going to be 5x squared. Cancel 9 fifths. So here's the thing. Again, think about this analogously. Just as in Calc 1, you're approaching from the left side, you get to some value. You approach from the right side, you get to some value. Say, hold on a second, that didn't approach the same thing I just approached. So it's broken. There has to be some sort of a jump in my or in my graph. Here we say, okay, so maybe I can't call it left and right because left and right is meaningless when you're talking about this plane. But say I'm approaching from specifically, I'm going along this, this y equals x path. I'm getting up to my point, and I'm approaching the surface value of 2. And okay, then I'm going to go on a steeper path. So instead of going on this, I'm actually going to somewhere else. But riding on that pathway is getting me to 9/5. Your surface is doing right at that point, which means that your limit doesn't exist. You broke it.
The only restriction to path that we choose is basically that we put y and x either as a 0 or equal 0. Or any equation that
Well, yeah, so the idea is you're always going to have, obviously make your life easier and just choose easy path. And the goal of this is you're just trying to find 2 paths that result in you having 2 different limiting points. So the easiest way to do it is to always start by saying y equals x. And so then the hardest part of the question is just finding a convenient second path to test that isn't going to be algebraically disgusting. The idea is 2 is not 9/5 as far as I'm concerned. So this lets us conclude. And then when you do something like this, you always got to cite y though. And since this is a theorem, you by the TPP, the 2 path test. So the limit does not exist by 2 paths. Very important. Wink, wink, cough, cough, the hand. Okay. Feel like you can do that?
Yeah.
And so you cite 9.905 specifically because the first path gave in. And you say you cannot equal 9 and
It can't approach these 2 different values simultaneously. Yeah.
So if we had found that both values do equal 2, that doesn't mean that the limit is 2. It just means that there is a limit.
Say it again for everybody because they weren't listening to you.
So if we found that both paths equal 2, that means that there is a limit, but not necessarily that the limit is 2.
Right. So again, this is a 2 path. This is a 2 path test for what?
Non-existent.
Okay. So say you're doing your work and you happen to choose a path that happens to give you a correspondence. Oh, it exists. No, not necessarily. So make sure, because just because it happens to work out, if you by some miracle you manage to find 2 paths that actually get you to the same thing, that does not guarantee the existence, because this is a test for what? So don't use a test for non-existent to try to prove existence of something. And it'll be given to you. So like the way that these questions will be given will be more like theorem style. It'll be like, this limit does not exist at this point, prove it. And don't stare at it and just go, oh my gosh, proof. And then brain just deletes, and then just be like, oh, 2 path test. I just got to do these 2 computations, and that suffices because there's a theorem for that. Okay, is that clarifying what's going on? Yes.
so the restrictions for y equals it's always has to be x with some constant.
Not necessarily. A path is basically, think about a path in plane. It's some relationship y is equal to some function of x.
Okay.
And that's the path you're taking to approach whatever point this point might be. The choice of x and qx is strictly for convenience. If you want to do y is equal to the sine of the natural log of the absolute value of the square root of x, sure, by all means, go for it. You'll get different values. But why suffer more when you could just plug in x? So if you choose some diabolical function and path to take into here for your 2 path test, that's not on me. You've been warned. This is the easiest way to go. Most reliable step is to just change the constant multiple. That's usually enough to do the trick.
And so just put across the last time. We're trying to prove for non-existence.
Yep.
So if we do get the same answers, that proves that a limit does exist.
Not quite. Don't use this to prove that something exists. Only use it to prove that something doesn't exist. So if say you happen to get 2 again, then I would just choose another path.
Okay.
I would then maybe say 3x or maybe 7x or something different.
And
Yeah.
so what happens if the limit did exist, what would happen if we did try to test what's non-existent?
Well, in that sense, I would be wasting your time. So the problem's going to be like, it breaks. So you're not gonna be given a limit that's like really, I know what your concern is, that you're gonna test like a bunch of paths and you're gonna keep getting stuck running into the same thing. That's not gonna happen. The kinds of things that they're gonna have you practice on will be pretty straightforward as you plug in. Yeah. They're not trying to trick you. They're just trying to make sure you understand. Use one path, use another one, approach different things.
But that would be given a problem saying, does this limit exist, test it with this test?
Right, no. I would never ask a question that asks for existence relying on a theorem about non-existent, because that inherently is an absurd question. So. But no, that's a good clarification, yeah. Anything else about this? Considering this is the cough, wink, wink, most important section for limits here. Cool. All right, we're gonna just talk about continuity real fast. And then I'll teach you what equals actually means. I figure that's something, if you're gonna get a degree from college, like, you're talking to your future grandchildren someday. Anyway. Well, let's say there's mathematicians were left alone for a little bit too long. And we came up with some pretty cool stuff. So. All right, so here is a definition for you guys. This should be analogous to something you already know. So when you see this, it shouldn't be like, oh, what is this? I'm seeing it for the first time. It should be like, familiar friend, you're older now, you smell a little bit worse, and puberty hit you, but I can still see, The function f is continuous at the point AB, provided some things are true. And so the easiest way to do this as a checklist, having experimented many different times with presentations of this definition, this seems to be the most effective. First of all, if you plug it in, it better exist. Like if you just plug it in and it's gone, then poop, not continuous. That's a pretty easy thing to justify. And then the second thing that we got to check is that the limit p goes to p naught of your function actually exists. Because again, why bother? If you know that the limit doesn't even exist, it's broken, why bother? It's not going to be continuous. So function actually has to exist at that point. You got to be approaching the same exact thing to that point. And lastly, we just got to make sure that the very thing we're approaching is the thing it's supposed to approach. So that's the limit p goes to p naught f of x, y equals f. I should specify that this is p naught. That's my bad. Familiar? Old friend. He's grown up a little bit. He's got himself a girl. Now they yeah. I like this checklist because it's very easy to tell. Well, what happens is people show something as continuous and something about the word show or like demonstrate more than just algorithmic processing. Just use the checklist. There is technically a more rigorous way to define continuity, but I won't bother you with that today. Okay, let's learn about zero or equals. Well, we can learn about both. All right. There's something called a relation. Do you guys know what a Cartesian product is? Okay, you don't realize you know what it is. So basically,
I remember the term.
R cross R, it gives R2. So it's the set of reals cross the set of reals. So this is going to generate ordered pairs where you have some real number, right? Okay. So the idea is suppose we have some set, we call that set X. Now what's gonna happen is we're going to take the Cartesian product of the set with itself. Okay, so what this means is that we've generated a set of elements X such that, or well, I'll tone down the abstraction. It'll be elements S, 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 or S prime, such that S and S prime are in S. Right? So you just say, hi Billy, hi Joe, we have the same mom, and then boom. Oh. Okay, now the idea is you take these Cartesian products, you don't necessarily there's certain Cartesian products that are special. This is specifically a set together with itself. And so you can take subsets of sets. And so what we do is we're going to take a subset of this Cartesian product. And so what we'll do is we'll define, so equals is defined to be, because you can't use equals anymore. You got a new symbol. This very specific subset. And it's the subset of the form X in a set, which is a subset of X product. So what this means is it's saying if I've got a collection of objects that some element X can only relate to X equals X, if and only if the ordered pair XX is in X. So if I take something in S, and then I take it in an ordered pair with itself, that is how we define equality relation. So whenever you see something like 4 is equal to 4, what this is saying for in R is that in the set of the reals, the Cartesian product R cross R, we have a subset of all of the numbers X comma X, where X is real. So it'll be every single form is going to give equality on reals. So that's why 4 is equal to 4. But the great reason why this is great is because S could be anything. This could be a collection. This could be a set of sets that have sets. It could be dogs, cats, and trains. You know, this could be your family members. This could be, so this is where algebra starts to take over everyday life. So when people do birthday party planning, they're doing algebra. When you make your grocery list, you're doing algebra. When you make a budget, you're doing algebra. When you make choices about who to exclude from your wedding because it's too expensive to have everybody there, but you want the important people there, it's algebra. So everything can be in some sense described by this abstract stuff because you get away from numerical reasoning and more into logic and relations. So, okay, that's equals. You guys enjoy physics.
Oh.